Our first speaker this afternoon is Lansing Horan IV, who is from the Massachusetts Institute of Technology in the field of plasma physics, and his practicum is at Sandia National Laboratories, New Mexico. Come on up.
All right, good afternoon. Thank you for the introduction. Today I'll be talking about the density structure of a radiatively collapsing reconnection layer using shadowgraphy. I'll start off with a brief overview of magnetic reconnection. Reconnection is a ubiquitous process that occurs in magnetized plasmas everywhere. When we have two counter-streaming flows of plasma carrying anti-parallel magnetic fields, like the situation you see on the left, at the center where the flows collide, we form a reconnection layer. This is just a name for the region of plasma where the magnetic fields are explosively annihilated. And thereby, we also form a strong electric current in this region. In this way, reconnection is an energy dissipation mechanism. We convert magnetic energy into kinetic and thermal energy. And my talk will be focusing on the effect of ohmic heating, reconnection heating, and the consequences therein. In particular, reconnection heating can drive strong radiative emission from a variety of astrophysical plasmas, such as those that you see here on this slide. There's a lot of theoretical predictions that high-energy X-rays originate from reconnection events that are happening constantly in these media. In particular, we're interested in the regime of strong radiative cooling, which you could see an inequality expression for on this slide. But the physical meaning of this is that as a parcel of plasma, or like as a bit of the fluid, is moving down the reconnection layer, even as it's being heated by reconnection, it still experiences a rapid drop in temperature due to strong and intense radiative emission. This cooling parameter that you see on the slide, this is just a ratio of characteristic timescales. This is just saying that with strong radiative cooling, there's a dynamic interplay between reconnection heating and radiative emission. Also, another reason that we're interested in this radiation is because from the point of view of observation here on Earth, it's impractical that we could ever visit most of these environments. They're too far away, they're too extreme. We can't ever probe them experimentally. So really the only signature of reconnection events are these high-energy X-rays. So this is all to motivate the benefit of having a test bed, a laboratory astrophysics platform to understand the fundamental physics of this process. One last reason that we're interested in strong radiative cooling is because it leads to instabilities in the plasma, in particular, the radiative collapse of the layer, which I'll talk about here. So initially, we have roughly a pressure balance between the thermal pressure of the hot layer from reconnection heating, in contrast with the magnetic pressure in the inflow plasmas to the left and to the right. So that hot region of plasma in the reconnection layer is going to emit X-rays. It wants to cool itself off, and thereby it's going to drop its temperature and, of course, momentarily drop its thermal pressure. But this only serves to allow for the layer itself to become compressed by those constantly in-streaming flows of plasma to the left and to the right. This compression momentarily, very rapidly responds and restores that pressure balance by increasing the density in that region. But the last little tidbit of this little loop is that most radiative cooling mechanisms, such as Bremsstrahlung emission, scale with the density squared. And so in the end, we have a positive feedback loop. We have only increased the original rate of radiative emission, and the layer itself collapses due to strong radiative cooling. This just means that the layer is getting colder and denser as time passes. And in the past decade or so, there's been a lot of recent theory surrounding radiative reconnection because it's very astrophysically relevant. And the bottom line is, one of the central goals of our research is to try to get experimental evidence of this effect in order to get hard experimental data, because it's really hard to show this sort of thing in the lab. So also in the past decade or so, there is an established platform using pulsed power in order to conduct magnetic reconnection experiments. This was established at Imperial College London on the MAGPIE pulsed power facility. So it all begins on the left. This is called an exploding wire array. And for reference, it's on the order, it's about the size of a ping pong ball, maybe even a little bit smaller. And what we do is we field this as load hardware on a pulse power machine, and we drive a strong electric current through it, on the order of about 1 million amps of electricity after just a few hundred nanoseconds of rise time. You can see the current path in purple through this array. So the impact of this strong driving current is we ohmically heat those little tiny wires that surround the array. And so thereby we vaporize and we ablate the outer surface material, forming coronal plasmas around each wire. Also, with this configuration, with the current path, we induce an azimuthal magnetic field, shown in blue, and thereby we have the J cross B accelerating force, where we drive those plasmas radially outwards away from the wire array. And so lastly, if we place two of these arrays next to each other, and if we use a pulse power machine to drive them in parallel, then at the center, we have a reconnection layer. We have counter-streaming flows with anti-parallel magnetic field. So all of this is good, and there's been a lot of good research in the past decade with this platform on university-scale machines, which again, about 1 million amps of electricity. But in order to drive more interesting instabilities in the plasma that are astrophysically relevant, this scale is a little bit limiting. And so that motivated us to go bigger. So this is a picture of the load hardware, or really a graphic, called the magnetic reconnection on Z, MARS, which is basically just taking that hardware, making it bigger in order to use it on the Z machine, which is the world's largest pulse power device at Sandia National Labs. And so bottom line, we have bigger arrays, we have more wires, we have denser plasma, we have more magnetized plasma, we have a higher energy density regime where we can more effectively drive the instabilities that we're interested in. And the last thing I'll say is that we're moving from 1 million amps of peak current up to 20 million amps of peak current, so more than an order of magnitude increase. But all that said, that was kind of the background. So what I said is that I'd like to gather experimental evidence, actual data, of this radiative collapse process. So I'd like to measure the density structure of the reconnection layer plasma. So this means that I need to resolve some sort of measurement spatially, because I want inherently a structure measurement. But I also need temporal resolution, because I need to measure this dynamic process of radiative collapse. So the question is, how can I use the Mars experiments, and how can I use a diagnostic to make this sort of measurement? So just for some background, a general principle that we all are familiar with is the refraction of light. A simple example you can kind of see here. We've all been outside on a hot day, bright and sunny. There's a pool. Whenever sunlight travels from the air and it crosses that medium surface between the air and the water, those little waves at the top of the pool bend the light at that interface. And so at the bottom of the pool, that bottom surface, we see bright regions and dark regions of light. So this is the general principle behind the diagnostic that we're using to make this measurement, which is called shadowgraphy. So shadowgraphy, the idea is just you take some sort of probe beam, you pass it through a medium, and then you take an image of that probe beam after it's traveled through that space. What I'm showing here on the right is from decades ago. This is a photo from NASA. This is a shadowgram image. This is a small toy model of a re-entry vehicle that they fielded in a supersonic wind chamber, and they took this sort of shadowgraph image. So you can see at the interfaces where the refractive index has changed, which is where the density of the air is changing, you can see patterns of light and dark at the shock front and also the turbulent plume behind the object. So in our case, if I'm doing shadowgraphy for this experiment, in our case, the probe beam or the light source is a laser, and our medium is the plasma, the reconnection layer plasma. You can see on the far left, we're looking at our system from the top down. We have the wire arrays to the left and to the right. And at the center, we have that reconnection layer plasma. So during the course of our experiment, which lasts less than a microsecond, less than 1 millionth of a second, then we carefully time that probe beam to shine through the layer. And then we want to take shadowgraphic images of what happens to the probe beam, which is, again, is just a fancy way of saying we want to take a cross-section of that laser beam intensity profile. So initially, notionally, the laser beam is kind of uniform. It's flat before it passes through the plasma. But then you can see at the bottom just some sort of example that the density gradients in the plasma will serve to deflect or refract those rays of light outwards away from the density gradients of this object. And so it is these objects that encode information about the density structure. So Mars4 was one of our 5 Mars shots that we've conducted over the past several years, and this was the very first Mars shot with Shadowgraphy. It was also the first Mars shot that I had the honor of being a part of. And I just want to briefly go over how we configured the laser imaging on Z, or LION's, Shadowgraphy diagnostic. So first, I'm plotting as a function of time the current drive. So this is the electric current that the Z machine drove through the wire arrays. And for each wire array, we peaked at 10 million amps of electricity after 300 nanoseconds of rise time. So it's this current that's really generating the plasma and kickstarting our experiments. We also fielded X-ray diodes in order to measure the time series of basically high-energy K-shell emission from our aluminum plasma in order to kind of characterize when radiative emission is happening. And so you can see by this pulse in blue that the peak of this emission occurred at about 220 nanoseconds after the start of our currents. And so with this information, this informed how we selected for the laser pulse to shine through the plasma. The 4 green dots that you see on that screen are the 4 points in time that we collected shadowgraphic images of our reconnection layer. And again, this was intended to measure the effects of radiative collapse because, again, this is coinciding with that radiative emission. So first, I'll show you one of the 4 images that we collected on this experiment. And again, to orient you, you can see on the right our load hardware geometry. So we're looking at our reconnection layer from the side. So there are a few image features that we can immediately see. So first, at the center, we see this dark central void. This is the result of that dense reconnection layer that is refracting light outwards away from the center. We also see bright intensity bands outside the layer. And from simulations, we believe this could be due to MHD shocks in our system. And then lastly, we see some evidence of axial non-uniformities, small little perturbations throughout this field of view, which could be consistent with the presence of instabilities in our system. So now I'm showing all 4 images that we collected. Again, the 4 points in time spanned about 40 nanoseconds, give or take, which again is surrounding that X-ray pulse. So the first image was at the beginning of the X-ray pulse, the middle 2 are kind of near the peak, and then the last one is toward the end of that radiative emission. So this data is super cool, super exciting. These are the first shadowgraphic images of a radiatively cooled reconnection layer. Very niche field, but we got it. And so now the real question is, shadowgraphy is typically a qualitative diagnostic. And so again, I told you I want to make a measurement. So how can we move to the quantitative? How could I actually get parameters of the layer structure from an image like this? And so, for example, I could look anywhere on the image. I could get an intensity profile. And the question is, how do I use this intensity profile to measure the density and the width of the layer? So it's kind of a 4-step process. If you start with step 0, which is just the background of how I'm going about this, I'm taking a forward model approach where I have a piecewise ray tracing algorithm. It's a semi-numerical, semi-analytical approach. I have an elliptic Gaussian model with 4 parameters: the density jump, width of the layer, length of the layer, and then some small tilt angle between the beam and the layer itself. And then for everywhere in that 4D coordinate space, I can numerically solve for an intensity profile, one example of which you see in the upper right here. Also in the bottom left, maybe it's a bit hard to see with the screen, but I'm plotting in green individual ray paths as they traverse through this plasma. And you can see, again, that effect of light being refracted, light being bent as it's moving through these density gradients. And then I'll skip this for the sake of time. Long story short, things are faster, numerical methods are good. Cool. OK, so then this brings us to the real step 1. So using this model as the foundation, I want to generate a large parameter space in this 4-dimensional plane that I've created. So I want to generate tens or maybe even hundreds of thousands of reference intensity profiles, where on this slide here, if I move from left to right, I vary the width of the layer. And if I move from the top down, I vary the density jump of the layer. And you can see at each point, at each coordinate in this 4D space, I have an intensity profile. And so I could use this in order to try to reconstruct the density structure by basically profile matching. But first, step 2, this is a very quick proof of confidence or just like a sanity check, where I just want to demonstrate the idea behind profile matching. So the idea here is if I have a perfect scenario where I'm feeding in a signal that I generated from the same model that I used to generate the library, can I get out what I put in? Can I reconstruct that density structure? And there's a lot going on this slide, but the main takeaway is that there is not necessarily a unique measurement from Shadowgraphy. I'm looking at a solution space of plausible layer parameters rather than a singular measurement. So the last step that I'll talk about is this final step. These are preliminary measurements using quantitative Shadowgraphy on the actual experimental data. And again, I have 4 images. I'm showing just one image here, one point in time. And you can see I'm resolving that spatial coordinate z prime. So I could take lineouts arbitrarily across that z prime space. And what we see here is as the color changes, these represent the 4 frames, the 4 points in time. And then along the axial height, those are the positions on the image. So again, there's a lot going on, but broadly speaking, we see consistencies with radiative collapse. We see the density jump is increasing as time passes. And similarly, we can plot the measurements from the width of the layer, which there's a little bit more scatter, there's a little bit more error bars in this, and I'm trying to clean that up. But we do see evidence of the layer itself becoming thinner as time passes, which again is very exciting to see for the first time. The last thing I'll say is a very sincere thank you to everyone involved, DOE, NNSA, Krell, everyone involved in this fellowship. It has truly been an honor. I am very, very proud to be a part of this community, and I hope to remain in it for a long time. So with that, I'll leave it on the summary, and thank you for your time.